So I'm going to be talking about unitary property testing, lower bounds by polynomials. This is work by Adrian and Henry, but unfortunately neither of them could be here, so I'm giving this talk in their stead. So I'm going to start by trying to motivate why why unitary property testing is an interesting thing to do. Then I'll go into some of the works in this paper, particularly the lower bound methods. And then we'll talk about some quantum proof type stuff, like applying these polynomial method techniques to some complexity problems. Oh. So before I can motivate unitary property testing, I'm going to talk about quantum Curie complexity. It's kind of fitting that the last talk also was talking about this. So why do people care about the quantum Curie model? Well, for the most part, it captures a lot of problems we think we would like to do with quantum computing. For example, before I say that, I'll explain what it is, but the previous talk explained this too. So in the quantum Curie model, you're given Curie access to a Boolean string x. You can think of it in the way that you provide an index I, and it spits out for you the ith index of that string. So this model captures a lot of things we would like to do, in particular like unstructured search, Grover's search, and quantum period finding, which is the main subroutine in Shor's algorithm. And also adds more structure to a lot of problems. And by that, I mean we can actually prove lower bounds against the quantum Curie model, which allows us to show it allows us to limit the power of certain models. In particular, like we can show lower bounds against quantum algorithms in the Oracle model, which basically limits quantum advantage. So there's two ways we do these lower bounds. The first one is the adversary method, and the second one is this polynomial method. I won't talk about the adversary method here, but the polynomial method was first introduced by Beals et al. In 2001. Basically, if you show me a quantum algorithm that's making calls to some oracle, and you write the accepting probability of that algorithm as p, and the x's there represent the oracle, then the output probability is some polynomial in the x's that's at degree at most 2t, where t is the number of oracle calls that algorithm makes. So in particular, if you want to lower bound the runtime for some problem, all you have to do is tell me that that problem itself is not approximated by any low degree polynomial. The quintessential example is quantum OR, which is Grover's search, for which you can show there's no polynomial degree square root of t that approximates it, which gives the Grover search optimality. Unfortunately, we're quantum people, so we're not satisfied with doing classical problems. There's a lot of quantum problems you also want to do that can't be described classically. In particular, you might be running some experiment and you might have some unitary process that you make queries to, but that process might not be something you could even talk about classically. Another thing to note is that, as you would expect, the standard Curie model is encompassed by this model simply by making the unitary flip the phase of the ith index of the string. Some of the problems we want to do are kind of classical looking. Here's one of them. In this example, you're given access to a unitary that flips the phase for some subspace, adds a negative sign for some subspace, and we simply ask if that subspace is high dimensional or low dimensional. If you think of the subspace as being some subset of strings, then this is equivalent to asking is the Hamming weight of that string big or small, and there's some promise gap there. And for these types of problems, we can simply use the lower bounds against a classical problem to find lower bounds for these ones. But there's lots of problems that are really fundamentally quantum. So I'm going to go through three of them. The first one is this unitary recurrence time. Basically, you have some access to a unitary process, and you want to know if you run it for t times, does it go back to identity? Does it have a cycle of length t? Another one you might think about is, well, now we have the similar oracle from the last problem with dimensions, but it only flips one state, and we're curious about if that state is highly entangled or if it's a product state. And the last one here is just you have a unitary that is some Hamiltonian evolution, and you want to know if that Hamiltonian, in this case it says geometrically local, but you could ask about any property of the Hamiltonian that some system is evolving under. For these types of problems, we're not going to be able to use the classical lower bounding techniques, so we'll have to come up with some inherently quantum strategies. And finally, I guess I'll also try to motivate this study by telling you that lower bounds against classical oracles yield some very interesting separations between complexity classes. In particular, if you know that a particular model can or cannot do a classical oracle problem in a certain number of calls, you can design oracles that essentially separate those classes. So the example here is that because Grover can't be done faster than because of the optimality of Grover, you can find an oracle separation between BQP and NP. And then, so we expect that by finding lower bounds against unitary property testing problems, you can find oracle separation between different quantum complexity classes. And this was also used in the past to great success. Aronson and Kuperberg showed that there's a oracle separation between QCMA and QMA. And as we will see later in the talk, the main goal of this line of work, at least this paper, was to get an oracle separation between QMA and QMA2, which I'll explain later. The contribution of this paper is a generalization of the polynomial method to these kinds of settings where you're allowed to query an oracle. In particular, if you have an algorithm that makes oracle calls to a unitary oracle, you can express the accepting probability of that oracle as a polynomial in the entries of that unitary and its adjoint. And the degree of that polynomial will be at most 2t, where t is the number of queries you make to the oracle. Now, I will point out, similar to the classical technique, this is a very multivariate polynomial. There's going to be 2d squared entries. And there's not really good techniques for lower bounding those. But this is also true of the classical case where you would have a high degree multivariate polynomial. And there's lots of tricks we can do to try to reduce the number of variables that are in the polynomial. In particular, we can exploit symmetries. We can, try filling in some variables and reducing the number of variables like that. So I'm going to go through the three problems I'd mentioned before, basically show you guys some lower bounds and some upper bounds. For this unitary recurrence time problem, we notice that if I multiply the unitary by any v, I actually preserve that property. You can imagine taking v squared and then the v, u squared, and then the v and the v adjoint was canceled in the middle. And so if u squared is equal to identity, then vu v dagger would also equal to identity if it was squared. So this gives us a nice symmetrizing property. So instead of being dependent on all the entries of u, we can only think about a polynomial in the eigenvalues of u. So that kind of gets us back to the classical case. And we can write this theorem here, which is that instead of being a polynomial in the entries of u and u dagger, it's only a polynomial in the eigenvalues of u. And it's also symmetric, so permuting the eigenvalues doesn't change the answer. That's not necessarily a surprising thing, but it's nice that it's a nice trick we can use to reduce the dimensionality, reduce the number of variables in the polynomial from d squared to d. And this, of course, holds for any property that is invariant under unitary action. Using this technique, we can find a lower bound for the recurrence time problem. It's given here. I will contrast this with the upper bound, which it looks similar, but of course the two terms are multiplied instead of taking the max of them. For this other problem, this entanglement entropy problem, which is the one where we flip a state and we're curious about if that state is high entropy or low entropy, we also note that this problem is invariant under these other kinds of unitaries, basically tensor product of two unitaries, because along the split, you can't add or destroy entanglement if you only act on each part independently. And this leads us to another of these kind of symmetrizing theorems. Basically, if you're invariant under these local unitaries, you only depend on the eigenvalues on one half of them, this reduced state rho. This gives us a lower bound for the entanglement entropy problem, which is exponential in A. I guess A is the entropy that we're asking about, so either the entropy is less than A or greater than 2A. in general, we can start talking about groups and imagine we're symmetric under some group action and try to get a lower bound there. In particular, what we find is that if your property is invariant under the action of all of the unitaries in some subgroup, then we can express the accepting probability as a G invariant polynomial with the same degree as we had before. Yeah. And the other two things I talk about are just particular examples of this. So another reason we like to study these problems as complexity theorists is that, as I mentioned, having lower bounds against certain certain lower bounds in certain problems allows us to find separation between complexity classes. And then a lot of these classes we're going to be dealing with involve quantum proofs. So you could imagine, instead of just having Oracle access to your unitary, you're also given a quantum proof state with some number of qubits. And we would be curious in, can you do better than just having Oracle access to your unitary? So this kind of motivates this question about, do quantum proofs provide speed up? So in particular, we can apply these polynomial methods similar to how they're applied for the classical oracles to a lot of these problems. So for the recurrence time problem, if you're given an m-qubit quantum witness, we can actually show a lower bound of the max of square root of d over m and t over m. And similarly for the entanglement entropy problem, we have that I guess you can move the m to the other side. So for that problem, you have to make at least exponential in a over 4 divided by m curious to the oracle. And I guess to give a little bit insight of how these proofs are done, there's a nice method by Aronson which is called the guessing lemma. Basically, you can convert any oracle with a proof into an oracle without a proof that just guesses the proof at the cost of essentially making the accepting probabilities really, really small. But you can still use the polynomial method for that with those new accepting probabilities. That's where all the factors of m come from. The last thing I'll talk about in this talk is going to be this new class, or not really new, but new to this talk, called QMA2. In particular, in QMA2, with parentheses 2, the quantum algorithm is given an unentangled proof. So it's given the promise that the proof string it's given is bipartite and it's not entangled across the cut. And of course, QMA is contained in QMA2 simply because you can ignore 1/2 of the proof state and just use that on its own. And QMA2 is a fascinating class because almost nothing is known about it, even though it doesn't seem that different than QMA. If you could show that QMA and QMA2 were separate, this would be a negative answer to the disentangler conjecture, which is basically asking you, is there a process you can do that takes a polynomial number of input bits and outputs a separable state on fewer qubits? Just to give context there, I think there are exponential, if your input state is exponential in size relative to your desired output state, there are known ways to do that, but no one knows how to do that with a polynomial sized input state. And this is kind of the crazy part, which is the only inclusions we know about QMA2 is that it's bigger than QMA and it's less than nexp, which is a huge class. So we would really like to be able to say something about QMA2. And just to give evidence that QMA2 is separated from QMA, there are short proofs for 3-sat in QMA2. So if you promise me that the proof is going to be disentangled, there's a square root of n sized proof. And there's no way that you could have that short of a proof, assuming the exponential time hypothesis. So, I guess the state of the field is we kind of think QMA2 is its own thing, but no one knows how to prove things about it. In order to take steps towards proving that, we introduced this problem called the entangled subspace problem. Basically, it's very similar to the entanglement entropy problem, but instead of having a single state that we flip the sign of, we take a projector onto some subspace, and we ask whether or not that subspace contains an entangled state, or if all of everything in the subspace is a product state. The reason why we believe that this can be used to prove oracle separation between QMA and QMA2 is that there is an efficient QMA2 verifier. In particular, you can be given a product state and simply verify that it's in the subspace. And there are reasons to believe that it's not possible by QMA verifier, although this paper was not able to show that. It was able to show a lower bound against QCMA, and it explored some other average case versions of the problem. I guess just to give more context on this, in the case where P is low dimensional, so if it's rank 1 or smaller, or like some constant, you can actually convert a QMA2 verifier into a QMA verifier. So if you wanted to find an interesting instance of this problem, you would have to explore very high dimensional subspaces. And the other thing is that the QMA2 verifier, I think, only works when the A is small. In particular, I think that kind of breaks the proof that they were going for. So, yeah. There's a bunch of open problems here. Obviously, I've mentioned a few. The most recent one that I just said is to prove a strong lower bound for the entangled subspace problem. So, as I said, showing this would be a huge leap forward in our understanding of QMA2. It would also refute a couple of conjectures. The belief is that, the entangled subspace problem is another problem that's invariant under local unitaries. So, we believe that exploiting these symmetries can get similar lower bounds to the other problems I had mentioned in this talk. Another open problem is to prove tight upper and lower bounds for unitary property testing problems. The one that I'd mentioned was the recurrence time problem, where there's a slight gap between the upper and lower bounds. So it would be nice for someone to make those the same. And, more generally, you can wonder if this generalized polynomial method can be used for other kinds of oracle models. For example, if the oracle is non-unitary, or if it doesn't have nice unitary, local symmetries that you can exploit, can you still make claims using the polynomial method? And of course, I'm not the one who did this work. So if you have, questions that you didn't get to ask here, please email Adrian. His email is here. That's my talk. Thank you.
Are you actually willing to answer questions?
Yeah, I'll try.
Okay. Any questions for the authors or their representative? Let's see if I can reach you.
Thank you for the talk, John. So this is a question that's maybe not specific to this polynomial method, but to the polynomial method in general. So this assumes that you can query the oracle as part of a quantum computation, right? So I can query it sequentially with an auxiliary system. I can perform global multi-copy measurements at the end. Mm-hmm. Do you know whether the polynomial method has anything interesting to say if I restrict something here, like if I can't query sequentially but only in parallel, or if I have to do single copy measurements, or is that not the strength of this method?
Well, certainly if you can only query the oracle in parallel, the way that the polynomial method works is basically you write out each entry of the matrix, and as you have to conjugate by the oracle unitary and your own unitaries, you end up building up the powers of your entries. So I would assume if you did something like restricted the types of measurements you could do, that wouldn't affect it, because it's the upper bound on the degree of the polynomial. But maybe if you said you only allowed to query the oracle in parallel, you wouldn't end up with this layered, where the power increases each time you query it. Yeah. Okay. So depending on the restriction you make, it may or may not affect things. I guess that's not a great answer, but yeah.
Thanks.
Other questions? Let me ask a question about the third bullet here. Is the question here whether the polynomial method can be generalized to such matrices, or do you already know that you would get low-degree polynomials in the entries of the matrices? You just don't know how to use the method.
Yeah, so the proof of the polynomial method in this paper is very similar to the proof of the original one, basically writing out each entry and showing that it's just a polynomial in the entries there. So I assume that would work for non-unitary and also the other types of things. But that polynomial method by itself is not very powerful. You need to pair it with symmetries or ways to reduce the number of variables, right? So if you don't have those techniques, you can't really say much because there's very little that's known about the degree of multivariate polynomials. So the question I think here is like, if you gave me some particular group symmetry, like, can you like use that in a powerful way? Yeah, so I think that the polynomial method is a great framework, but it needs to be paired with some ingenuity on the polynomial side. So that's really where the brain power comes in.
Thank you. Anybody? Okay, let's thank John and all the speakers of this session.